Hello everyone. In the last video we came up with an optimized clock tree. So basically what we did was the number of buffers that we had used for the previous clock tree or for the previous edge tree, we reduced the number of buffers and tried to came up with a tree so that each and every buffer are used to its fullest capability. So that was the thing that we did in the last video. And on what basis was that done? It was on the basis of the short circuit current and the load capacitance. So basically we tuned the load capacitance of each and every buffer in such a way that first it should be able to drive the load which is the capability of this particular buffer to drive, and second we have also taken consideration into the short circuit current, basically from a power angle. So we have tried to look into all those in the last video. In this video, since we have since we have built the clock tree, so in this video let us try to look into the latency and the power number what we see in from this particular clock tree. Let us not try to look into this skew, pulse width and duty cycle again, because more or less they will remain the same. You can try it out as an homework kind of thing. In this video let us try to come up with the latency and the clock tree power for this particular clock tree, for the optimized clock tree, that as we say it's an optimized clock tree. Let us try to see how much optimization have we done. So we'll start with latency first. So latency, initially it was 9 buffer delays plus 10 wire delays. And now in this case, if you calculate the latency, let's say the delay required for the clock signal to traverse from this clock port to this clock endpoint, let us try to calculate that value. So it's like 1 2 3 4 5 buffer delays plus 1 2 3 4 5 6 wire delays. So in this case the latency will be 5 buffer delays plus 6 wire delays. But there is a catch over here, and the catch is initially the buffer, by the equation it looks like we have reduced the latency, but actually it's not. It's kind of not completely reducing the latency, because the buffer delays in the initial case, these buffers were placed very close to each other. So in that case the buffer delays were very fast. By fast I mean the output load and the input transition were so sharp that these buffer delays were very fast. The buffers were very fast. In this case, the buffers that you are seeing over here, it will see a different input transition and a different output load. So the value of and in this case it's a bigger load that each buffer is seeing. So the delays will be high over here, but only the advantage is the number of buffers that we're using is less compared to the previous one. So that kind of balances the buffer delays and the buffer delays between this clock tree and the previous one. And similar goes for the wire delays also. Initially we had how much? We had like 10 wire delays, but now we have 6 wire delays. The difference is the length of the wires have changed. In this case, the length of the wires are a bit large compared to the previous one. So the wire delays pretty much more or less gets optimized, gets balanced out over here. So it gets cancelled out. So let's not focus on the latency from the latency aspect. So now let's try to look into the clock tree from a power aspect. So now so the P total over here, initially it was 39 multiplied by dynamic power plus the short circuit power plus the leakage power. Now in this case, let us try to calculate the amount of the number of buffers that we have. So let us try to start from this leg. So it's like 1 2 3 buffers over here, and 3 multiplied by, we have similar 4 legs, so 4th is a 12, and the remaining buffers are this 13 14 15 16. So we have 16 buffers. So total power has reduced from 39 the complete power into 16 into the complete power. So it's a huge reduction in the amount of power that we are saving. So it's like more than 50% amount of power that we are saving. The amount of power that has been saved by optimizing this particular clock tree is tremendous. It's actually huge. Why I'm saying it's huge? Because this is the amount of power that has been saved for 16 clock endpoints clock tree. Imagine a clock tree which would have been like 8 to like millions of flops, if there would have been millions of flop, then there would have been millions of clock tree endpoints that we would have optimized for, and the amount of power that gets saved for that amount of clock tree endpoints, it's huge. So in that, so if now we can understand that how saving how removing one buffer, or basically how using less number of buffers impacts directly the total clock tree power. And by saving the clock tree power, you actually save the amount of the complete chip power, because the clock tree power consumes like 70% of the complete chip power. In this case, if you have so basically building a clock tree, or smartly building a clock tree, will actually help a lot in the future. Like we will be saving an amount of power, and that's what the concern of the future VLSI world is being. So this is a point that we have to take care about, and this is the thing that we need to look upon, apart from timing and area. So this is one aspect from which we have to look into whenever we try to build a clock tree. So so this was all about the clock tree, or the optimized clock tree for 16 clock endpoints. Now let us try to look into a different kind of tree. Let's try to look into that. So in this case, what was the advantage that we had was the clock tree was very evenly spread. The clock endpoints were very evenly spread. Basically, if you see the clock endpoints, the 4 clock endpoints which are sitting over here, they were repeated three times. One was here, one was here, and one was here. So basically, the spread was very even. There was a very equal, and it's a very ideal clock tree that anyone can have, that any chip can have. But in a case where the clock endpoints are not as ideal as this one, but they are spread out randomly, in that case, what would be the catch? So if, for example, something like this. So if you have a chip, and this is how normally the chips are, it's even more complex than this one. So let's look into the same 16 clock endpoints, but they're not evenly spread, but they're unevenly spread. They're very irregular. The spread, if you look, it's like some over here, some less clock endpoints over here, something like that. So in this case, what will be the technique that you will be using for a clock tree? So what we'll do is, since this is a new topic that we need to enter into, we'll try to stop over here, and we'll start at the from a new topic where we'll be trying to build a clock tree for 16 clock endpoint again, but the spread of the clock endpoints are very uneven and very irregular. So let us try to build a clock tree for this kind of situations in the next video. Thank you.